video number 8 in a series looking at Advanced Higher Physics past papers, and this time it's the turn of stellar physics. So we're going to the Calder High School website and we're going to have a look firstly at the 2019 paper. We're looking for a stellar physics question, and that is question number 7. And one thing you might see in stellar physics questions quite often is a Hertzsprung-Russell diagram. And there's one there. Now, it's not a map, it's not a timeline, it's a chart that is showing you how the luminosity compares to the surface temperature, and also shows you how these stars are grouped into different types. And oddly, on an HR diagram, the temperature increases from right to left. So the hotter stars are on the left-hand side of that diagram. And the reason for that is that the peak wavelength emitted by the stars is usually shown on the x-axis as well, and the wavelength increases from left to right. So the longer wavelength red stars are on the right-hand side, and stars that emit a peak wavelength with a shorter wavelength towards the blue end of the spectrum are on the left-hand side of the diagram. Anyway, what are we asked here? We're told stars are classified depending on their position on the HR diagram, and 4 stars are labelled on the HR diagram. Which one of the stars is a red giant? Well, let's put the different groups on the diagram. You've got your dwarfs down the bottom left, your main sequence runs diagonally, and then you've got your giants and your supergiants. So a red giant will be in this region here. And so of the 4 stars that are labelled, it must be star D that's the red giant. Part 2, at present the Sun is a main sequence star, and it's predicted that it will eventually become a red giant. State the change that will occur in the fusion reactions within the core of the Sun at the point at which it leaves the main sequence. Well, only one answer that's acceptable here, and that is that the hydrogen fusion stops in the core. And part B, explain in terms of gravitational force and thermal pressure why the diameter of the Sun will increase as it becomes a red giant. Well, thermal pressure is acting outwards, gravity is acting inwards, so the thermal pressure outwards must be greater than the gravitational force inwards. Let's have a look at the marking instructions. Again, you'll get them from the Calder High website. It's a 2019 paper, so we're looking for the 2019 marking instructions. They're there, and we're looking for question 7. So, 7A part 1 was star D, part 2A, the fusion in the core stops, and part 2B, the thermal pressure exceeds the gravitational force. It's not often you get 3 1-mark questions to start with, and not a lot of writing involved. Anyway, let's move on. 7 part B. Betelgeuse is a red supergiant star in the constellation Orion, and it's 6.1 times 10 to the 18 metres from Earth, and it has an apparent brightness of 1.6 times 10 to the minus 7 watts per square metre. And we have to calculate the luminosity of Betelgeuse. Well, we're looking for a relationship that's got luminosity and apparent brightness in it. And it's this one here, B equals L over 4 pi d squared. Now if you're looking at an old version of the relationship sheet, it might say B equals L over 4 pi r squared, but it was changed to a d in 2019 because it's the distance from the star. And if you rearrange that for L, you'll get L equals B times 4 pi d squared. And then if we substitute the values in, the apparent brightness is 1.6 times 10 to the minus 7, and that's multiplied by 4 pi times d, which is 6.1 times 10 to the 18, and don't forget to square that. Do that in your calculator, you'll get 7.5 times 10 to the 31 watts. Now, I stated the relationship, then rearranged the relationship, and then subbed in the values. The SQA marking instructions always substitute the values in before rearranging it. And that's a better way of doing it, because you'll get 1 mark for the relationship, 1 mark for substituting in the values, and it's the final mark that's for the rearranging and the calculation and the final answer with the correct units. So if you make a mess of rearranging it, you'd still get 2 out of 3 if you substitute the values first. It's worth thinking about. Anyway, back to the question. Part 2. The radius of Betelgeuse is 8.3 times 10 to the 11 metres. Calculate the surface temperature of Betelgeuse. Well, we need a relationship that's got luminosity and surface temperature. So the one we're looking for this time is L equals 4 pi r squared sigma t to the 4. Again, I'm going to let the side down here because I'm going to rearrange it first and get t as the subject of the equation. So t will be the 4th root of L over 4 pi r squared sigma. And it's the 4th root of all of that thing, so let's bracket it. Now let's sub in the values then. So t will be equal to the 4th root of 7.5 times 10 to the 31 divided by 4 pi times the radius squared, and the radius is 8.3 times 10 to the 11, don't forget to square it, times sigma, which you get from the data sheet. It's a Stefan-Boltzmann constant, that's 5.67 times 10 to the minus 8, and if you do all that on your calculator correctly, you'll get an answer of 3,500 Kelvin. There's the SQA marking instructions. 1 mark for the relationship, 1 mark for the substitution. So there we go again. The substitution of the values has been done first, and the final mark is for the rearrangement, the calculation, and the final answer with the correct units. Substitute first, then rearrange. Good advice. Maybe I'll do that in future. Okay, part C. Ultimately, every main sequence star will become either a white dwarf, a neutron star, or a black hole. State the property of a star that determines which of these it will eventually become. Well, that's the initial mass of the star. There's the MIs, you just need to write mass. That was the 2019 paper. Let's have a look at another one. This is the 2017 paper, and the stellar physics question is question number 6. So it's another Hertzsprung-Russell diagram, which has got luminosity on the y-axis, temperature on the x-axis, and again notice that the temperature is decreasing as you go from left to right, and that's because the peak wavelength that the star emits is increasing as you go from left to right. The stars are more red on the right hand side. So part A, all stars on the main sequence release energy by converting hydrogen to helium. This process is known as the proton-proton or PP chain, and one stage in the PP chain is shown. And we've got a proton plus another proton, which is changing into a deuteron. That's a hydrogen nucleus with 1 proton and 1 neutron. So one of those protons must have turned into a neutron. And to do that, it has to give out a positron. And also, to balance the momentum and the mass, it also gives out a neutrino as well. So particles X and Y, positron and neutrino, either way around. Part B, the luminosity of the Sun is 3.9 times 10 to the 26 watts, and the star Procyon b has a luminosity of 4.9 times 10 to the minus 4 solar units and a radius of 1.2 times 10 to the minus 2 solar radii. And on the HR diagram, we have to circle the star at the position of Procyon b. And if you make a mistake, there's always an extra diagram at the back. So, the thing that's important here are the powers of 10 for the solar units and the solar radii. So 10 to the minus 4 solar units, that's the luminosity, and 10 to the minus 2 solar radii. Let's have a look at the diagram. So 10 to the minus 4 for the luminosity gives us a choice of maybe 3 or 4 stars there, but 10 to the minus 2 solar radii gives us pretty much 1 star to choose from, because it's just over 10 to the minus 2 solar radii. If we look at the numbers again, So 1.2 times 10 to the minus 2. So it's just above the 10 to the minus 2 dotted line. And it was 4.9 times 10 to the minus 4. So it's just above the 10 to the minus 4 luminosity. That's pretty tricky. And B part 2, what type of star is Procyon B? Well, if it's down at the bottom of the HR diagram to the left of the main sequence, then it is a dwarf star, or a white dwarf. 6 part B part 3, the apparent brightness of Procyon B when viewed from Earth is 1.3 times 10 to the minus 12 watts per square metre. Calculate the distance of Procyon B from Earth. So it's a relationship for apparent brightness we're looking for. That's B equals L over 4 pi d squared. I'm going to rearrange it first. So D is the square root of L over 4 pi B. But remember, it's a much better idea to substitute the numbers first, so you can guarantee that you'll get the first 2 marks and then rearrange it. Anyway, we've rearranged it, so let's sub the numbers in. So D is equal to the square root of the luminosity. Now the luminosity was 4.9 times 10 to the minus 4 solar units. So we are going to have to multiply 4.9 times 10 to the minus 4 times a solar unit. Well, that's times the luminosity of the sun. And that is 3.9 times 10 to the 26. And that's all over 4 pi times B. So that's 4 times pi times, and we're told the apparent brightness is 1.3 times 10 to the minus 12. Now if you do all that carefully on the calculator, then you'll get the distance of 1.1 times 10 to the 17 metres. There's the marking instructions. The first mark was for realising that 4.9 times 10 to the minus 4 solar masses means that you had to multiply by 3.9 times 10 to the 26 as the mass of the sun, and then substituting that in along with the apparent brightness of 1.3 times 10 to the minus 12, and then rearranging and calculating that R is 1.1 times 10 to the 17. 4 marks. Okay, on to part C. This is another one of these unfamiliar relationships. You've never seen this before, so hopefully all we have to do is put the numbers into the relationship and work out the unknown quantity. So this expression can be used to approximate the relationship between a star's mass, m, and its luminosity, L. Now, L naught is the luminosity of the sun, and we could just use the number 1 here for 1 solar unit, and m naught is the mass of the sun. And this expression is valid between 2 m naught and 20 m naught. And here's the number we're looking for. Spica is a star which has a mass of 10.3 m naught. So let's write this relationship down again, and we'll substitute in what we know. L is what we're looking for. Now, L naught is the luminosity of the sun, and that's 1 solar unit. And we're looking for the luminosity of Spica in solar units, so we can sub in the number 1 on the bottom there. And that'll be equal to 1.5 times m, which is the star's mass, Spica's mass. Now, it's 10.3 m naught. So let's sub that in there. 10.3 m naught over m naught, and they cancel out. And that's to the power of 3.5. Now let's simplify that. So L equals 1.5 times 10.3 to the power of 3.5. And if you do that on your calculator, you'll get an answer of 5,260. And the units we're told are solar units. So you could put L naught in there because L naught is equal to 1 solar unit. Or you could just write solar units. Or, if we have a little look at the marking instructions, you can just leave your answer as 5260. Don't actually need a unit because you were told to express your answer in solar units. Anyway, there you go. That's a couple of stellar physics questions. If you're looking for some more, best place if you want to look for a particular key area is to use Mr. Davies' interactive PDF of past papers. And there's a link to that on the Calder Glen High School Physics website, and once again, many thanks to him for that wonderful resource. There it's there, all you have to do is scroll down and you'll get the key areas and the hyperlinks to the individual questions and the individual Advanced Higher Physics past papers. That's it for Unit 1. We've covered everything in rotational motion and astrophysics. Next time round, we're going to start Unit 2. That's quanta and waves. We'll see you in the next one.